Welcome to MOVITRAC LTE-B Plus Basic and Intermediate Training. This is session 10 and the final session of this class. Good job for hanging in there through this. I hope you've learned some things, and I hope you'll find this session very interesting as we wind up our discussion of field buses. In our last session, we learned about field buses and the MOVITRAC LTE-B Plus. We learned how to connect them. We learned about external gateways and some of the basic details of the hardware. In this session, we're going to shift gears and take a look at the software side of things, how you communicate with a MOVITRAC LTE-B Plus and make it do things over the field bus. So we're going to talk about field bus control. Now, I want to make a very important point on this. There are many different PLCs, many different programming systems out there, and obviously we can't get stuck in the weeds trying to deal with all the different possibilities. So, here's how we're going to approach it. Each field bus standard is different, but what you do to control the MOVITRAC LTE-B Plus over it is the same. The information you have to send from your PLC or other industrial controller to the MOVITRAC over the field bus is the same across all platforms. So we're going to focus on this, what you must do to control the VFD. We're not going to get into the details of specific PLCs and their programming systems. You'll need to look at the MOVITRAC LTE-B Plus documentation and also the documentation that comes with the different field bus cards. All right, so let's get into the details of what the MOVITRAC is expecting. First of all, let's go into how field bus control works. Let's just start with a generic field bus with a PLC connected to it and several VFDs. How does the PLC talk to the VFDs and tell them what to do? The answer is it sends them processed data words across the field bus. Processed data words are 16-bit binary numbers that travel from the PLC to the VFDs or travel back from the VFDs to the PLC. They contain information that controls the VFDs. For example, there are bits that you turn on and off in processed data words that tell the VFD to start or stop. There are also parameter values that travel across the field bus, things like the motor's speed, the ramp at which it should accelerate or decelerate, information like that. Now, one thing that we need to get very clear is how we label process data words. We need to understand that they're labeled based on the direction that they flow. Everything is labeled and viewed from the perspective of the PLC. Now, the first process data word type is the process output or PO word. It goes out from the PLC to the VFDs. That's a good way to remember it. And it carries things like commands and operating parameters. Process input words, or PIs, go to the PLC from the VFDs. In other words, they go into the PLC. So this is kind of the idea here. POs go out from the PLC to the different VFDs, giving them commands, telling them what to do. And then the PLCs report back with PIs, which provide status information so the PLC knows what's going on. That's the general picture of how field bus control works. Now, the MOVITRAC LTE-B Plus uses a control scheme called 3PD. What is 3PD? Well, I'm sure you can guess just from the name. It's a system where we exchange 3 process data words in each direction. So this is the particular setup used with a MOVITRAC LTE-B and B+. You have the PLC, you have the VFD, and they're connected by a field bus. The PLC sends 3 process data words to the VFD to control it. Process output word 1 is the control word. It contains individual bits that activate and deactivate features within the VFD. PO2 contains the speed, telling the VFD at what speed to run the motor. And PO3 contains the ramp, which tells the VFD how to accelerate or decelerate. Now, the VFD sends information back to the PLC in process input words. It sends 3 back. Process input word 1 is a status word. It contains information about what the VFD is doing. Process input word 2 contains the motor's actual speed at that particular moment. And process input word 3 contains the motor's current, how much current it's drawing. The PLC uses this information to know what's going on. So that's the basic idea of control. It doesn't matter if you're using one of the classic field buses. It doesn't matter if you're using the external gateway. This is what you're going to be sending from your PLC to your VFD and what you're going to be receiving back. Now, let's sidestep for a moment and talk about gateway communication. If you're using the external gateway rather than connecting directly to the VFDs over a classic field bus, the gateway uses a very slightly different scheme. It uses something called 24 PD control. And you may be thinking, what's the deal with that? That's a lot of processed data words. Well, yes, it is, but let me explain why. As you recall from the last session when we talked about the external gateway, you learned that the gateway has up to 8 VFDs on an S-bus field bus on one side of the gateway, and then a different field bus on the other side, like an Ethernet-based field bus. The PLC talks to that field bus, and then the gateway passes the traffic over to its local S-bus. Now, when you set up the S-bus, every VFD has an address. When you configure the gateway and it goes out and learns what's out there, it identifies these addresses. Now, let's say that we have 8 VFDs, which is the maximum number you can have on the gateway, and we've assigned them the addresses 1 through 8. Of course, you don't have to do this. You can use any numbers you like as long as they're unique, but it's generally better to number them sequentially, and I'll explain why in just a second. The VFD learns all these addresses, and then what it does is it communicates over the other field bus by sending 24 processed data words to the PLC and accepting 24 processed data words from the PLC. What it does, it assigns 3 process output words to each VFD and 3 process input words. There are up to 8 VFDs, so 3 times 8 is 24. So this is what actually happens. The lowest addressed VFD in the chain gets process output word 1, 2, and 3, and process input word 1, 2, and 3. So you'll use those to communicate with that one. The next address gets process output word 4, 5, and 6, and process input word 4, 5, and 6. And then it goes down the chain, each one getting 3 POs and 3 PIs, until you get to the last VFD in the chain, and then you have PO 22 through 24, PI 22 through 24. That's where the 24 process data words come from. The gateway is assigning 3 of each to each VFD. That, by the way, is why you're limited to only 8 VFDs on a gateway, because 24 PDs is the maximum you can send and receive with a field bus card. So I hope that makes sense. That's kind of an interesting little nuance, but you need to understand this when you get communicating so you'll be able to set things up correctly. All right, let's look at some of the details of processed data words so you understand them better. As I said, they are 16-bit binary numbers, so something like this. They have bits 0 through 15. Processed data words can perform one of 2 basic functions. Individual bits can have significance. In other words, they act like switches. So when you turn on individual 1 and 0s, you're going to be controlling features in the VFD, like enabling it or disabling it, clearing a fault. The VFD, when it sends information back, can also use this strategy to tell the PLC what the VFD is doing. The PLC will have to look at those individual on-off bits to know what's going on. So that is one thing you can do with processed data words. The other thing you can do is the bits can form a single binary number. These are parameter words, words that provide information to the VFD like its speed or ramp, or coming back from the VFD indicating what its current speed is. So these are the 2 functions that processed data words can perform. Now, an important concept if you're new to control systems, when you program control systems, they usually work with binary or hexadecimal numbers rather than decimal. Decimal numbers are the numbers we use in everyday life. They're based on tens, but programming systems often work with binary, just 1s and 0s, or hexadecimal numbers, which is called base 16. You have the digits 0 through 9, but you also have 6 letters, A, B, C, D, E, and F. It's a system that actually works better for programming because you can convert back and forth between binary and hexadecimal very easily. Now, if you're a PLC programmer, I'm sure you know this already. You're probably very familiar with hexadecimal, But if you're new to it, you may want to go out on YouTube and watch a tutorial on number systems just to get a little more comfortable with it. Now, control POs are usually created as binary numbers because they have individual ones and zeros that are turning things on and off. So the programmer usually creates the binary number corresponding to what needs to happen in the VFD and then converts the binary number to hexadecimal. Parameter POs are usually created as decimal numbers, for example, a speed and a percentage or RPM, and then those are converted to hexadecimal numbers to be sent over the field bus. So we're going to be doing a lot with hexadecimal and binary in the next few minutes, so I hope this makes sense to you, but if not, just keep listening and hopefully it'll make sense as time goes by. Now, what if you're not really very experienced with working with these? You're not comfortable converting back and forth. Is there an easy solution? The answer is yes, there is. Working with binary is easy if you use the calculator built into Windows. It has something called a programmer mode. If you click the menu in the upper left corner and change it from standard or scientific to programmer, it will work with binary and hexadecimal numbers as well as decimal. So change to programmer mode, and then if you want to work with a binary number, first you need to click where it says word. It may say D word or Q word when you start the calculator, so just keep clicking it until it changes to word. What this does is it limits it to 16 bits, which is the size of a PO or a PI. Then click binary to put it into binary mode, so click the bin section there, and enter a number. Bunch of ones and zeros, and then if you look over here, you can see the hexadecimal equivalent, which is 46. Now, if it has fewer than 4 digits, just add some zeros to the left side because everything you send over the field bus will be a 4-digit hexadecimal number. So 46 hexadecimal should actually be 0046. So that is how you convert from binary to hexadecimal with the Windows calculator. Now, if you're working with hexadecimal, you can use the Windows calculator for that too if you want to convert from decimal to hexadecimal. And the way you do it, again, you make sure it's in word mode by clicking where it says word until it changes to word. Then you click des up there to put it in decimal mode, and you type in the decimal number like 16,384. And if you need to enter a negative decimal number, you need to click the plus minus button on the screen. Don't use the one on the keyboard. That will give you a negative number. And then you'll see the hexadecimal equivalent right there. C000 is the equivalent of negative 16,384. Again, if you don't have enough digits, add digits to bring it up to 4. So this one already has 4, so you're good to go. All right, handy little tip here. You may be wondering, why was a 0x in front of those hexadecimal numbers? Well, this is something programmers often do. They often preface binary and hexadecimal numbers with either 0b for binary or 0x for hexadecimal. It's simply a reminder that we're dealing with non-decimal numbers. Just remember that preface isn't part of the number, it's just there as a reminder. So when you see these prefaces in this session, just remember they're cluing you in what the number type is. If you see just a number with nothing in front of it, assume it's a regular decimal number. All right, let's look at the control word PO1 that you have to set up to communicate with the VFD. There are 4 bits within PO1 that tell the VFD what to do, so we're going to identify these. The first 3 bits, 0, 1, and 2, control the VFD. These enable it, disable it, or make it stop. Bit 0 is control or inhibit. If this bit is a 0, the VFD is ready to run. If there's a 1 in there, you'll get a control or inhibit stop. Bit 1 is an enable or rapid stop bit. If you put a 0 in that bit, you'll get a rapid stop, and if you put a 1 in there, the VFD can run. And bit 2 is an enable bit and the normal stop bit. If you put a 0 there, you'll get a normal stop where it uses just a nice ramped stop. And if you put a 1 there, it will run. And then finally, bit 6 is a fault reset bit. If your VFD is faulted, you can clear it over the field bus by turning this bit to a 1 and then back to a 0, which puts it in clear fault mode and then back to normal mode. So let's look at a few examples here. If I send it this binary pattern, and its hexadecimal equivalent is 0006, the VFD will run. So this is what you send over the field bus to tell the VFD to start up. If I want to do a normal stop, I send it as 0002. This has the right bit pattern to make it do just a normal ramped stop. If I want to do a rapid stop, I send it all zeros, and that will do a rapid stop using the special fast ramp. And if I want to do a controller inhibit stop, which is often coast to stop, I send it as 0001. So these are the hexadecimal patterns you would send in P01 to do common VFD operations. Now, if I want to reset a fault, I would send it 0040, and then I would send it another pattern so that can reset a fault. All right, the next process output word, P02, is the speed control word. Now, this one takes a little explaining. It's slightly complicated because we don't send the speed as an RPM value. We send it as a percentage of the VFD's maximum speed. So you send it a number between 0 and 100% or 0 and negative 100%. If you send a positive percent, you turn clockwise. If you send it a negative percent, you turn counterclockwise. Now, you must understand this. This can be a little confusing. On the MOVITRAC LTE-B+, if you send it a value that is plus or minus 16,384, that corresponds to plus or minus 100%. So what you have to do is kind of scale your percentage based on this range of numbers. So this number line here shows what you're going to get for different values. So for example, if you send it as 0, obviously the VFD won't turn because that's 0%. If you send it a +1, a +2, a +3, you're gradually ramping up. When you get to plus 16,384, you're at top maximum speed in the clockwise direction. If you send it a -1, -2, -3, or up to minus 16,384, you increase speed in the counterclockwise direction up to 100%. Now, to create those negative numbers in hexadecimal, the Windows calculator will be a big help if you don't know how to do that by hand, and I urge you to use the calculator. So you'll be sending it a hexadecimal number between 0 and 4000 for a positive rotation, and 0000 and C000 for the negative rotation. Let me show you a few examples here just to cement this and also show you how to set all this up. If you want to turn in the clockwise direction, you take the speed you want to turn in RPM and divide it by whatever number's in your P01 parameter. You multiply it by 16,384. If there are any fractions, you drop them, and then you convert it to hexadecimal, and that is what you send over the field bus. To turn counterclockwise, you do almost the same thing. You divide the speed in RPM by the value in P01, multiply by minus 16,384, drop any fractions, and convert to hexadecimal. So let's see an example here. Let's say that our P01 value is 1800 RPM, and we want to turn 360 RPM clockwise. We take 360, divide by 1800, that's 0.2, in other words, 20% of the maximum speed. We multiply 0.2 by 16,384, and we drop any fractions. The answer is 3277. We convert that to hexadecimal with the Windows calculator, and it is 0 CCD. If we send that value, we should turn at 360 RPM clockwise. Now, if we want to go in the other direction, let's say we want to go at 900 RPM counterclockwise. We take 900 RPM, divide it by 1800 RPM, that's 0.5 or 50%. We multiply 0.5 times minus 16,384. That gives us negative 8,192, which if we convert it to hexadecimal, being sure to put it in minus mode, is E000. So that is how you set up the speed word. That is the most complicated of the three. So if that didn't make sense, maybe play this slide back over again. The last word is the ramp word. This sets how you accelerate and decelerate. So if you're going to send a ramp up or ramp down value, you send it in P03 as a time in milliseconds. And the shortest value you're allowed to send is 100 milliseconds. So for example, if you want to set the ramp to 3.5 seconds, 3.5 seconds is 3,500 milliseconds. Just plug that into the Windows calculator, convert to hexadecimal, it is 0 DAC. And that is the value which will give you a 3.5 second up or down ramp. We talked about this in our last session when we talked about setting up field bus mode, and remember I said that there were 2 control modes for each field bus type. If you pick 3, 5, or 7, the VFD does not use P03 for the ramp. It uses parameter 03 and parameter 04 in the VFD for up and down. But if you set P12 to 4, 6, or 8, the VFD will expect the ramp in P03. So if you want to use parameter-based ramps, set the VFD mode to 3, 5, or 7. If you want to use P03, which is more flexible, use 4, 6, or 8. If you are in mode 3, 5, or 7 and you send a P03 value, it will just be ignored. Now, the VFD sends 3 process data words back to report its status, PI1, PI2, and PI3. PI1 is the status word, and this reports what's going on by turning individual bits on and off. This first bit is the controller inhibit bit. If it is a 0, you're in controller inhibit mode. If there is a 1, you're not. The second bit is a ready bit. If the VFD is ready, it will send a 1 in this bit, otherwise a 0. The third bit here indicates whether it's listening to POs and responding to them or not. In other words, you're in a mode that's field bus control based. If there is a 0 here, it means you're not, but if there's a 1, it means you are. This bit here indicates if the VFD is faulted. If there's a 1 in there, the VFD is faulted. If there is a 0 there, everything's fine. And then finally, the last 8 bits form a number that is either a status number or a fault number. And this will report what's going on with the VFD. I recommend you look in the manual. It's near the end of the manual. It tells you what these numbers can be. So that is the status word. The PLC can use this to know what's going on. PI2 is the current motor speed, the actual speed. So the VFD reports its current speed back. Again, it's in percentage form rather than RPM. So this is a lot like PO2, the way it works. So again, the same range here. So if you get a clockwise speed back and you want to know what really is going on, you convert it to decimal, you divide it by 16,384 and multiply it by the PO1 speed to figure out what it is in RPM. And to convert it counterclockwise, you do the same thing basically, but you do have to convert it from a negative to a positive value first. So here's an example. If your PO1 speed is 1800 RPM and the VFD sends back 2F0E, you convert it to decimal using the Windows calculator or a program in your PLC, and you will get 12,046. You then take that, divide it by 16,384, which is 0.735. If you multiply that by the PO1 speed, which in this case is 1800 RPM, you're turning 1,323 RPM clockwise. And if the VFD sends back DE25, that's a negative number, you convert it to a positive number, which is 8,667. You divide it by 16,384. It's 0.529, so you're turning at 52.9% the maximum. If you multiply that by 1,800, you'll find you're turning at 952 RPM counterclockwise. So that is what either you have to do or your PLC program has to do if you want your speed in RPM. And then finally, PI3 reports how many amperes the motor is drawing, so it gives you an idea what the current draw is, but it doesn't report it in actual amperes. It reports it as a percentage of the VFD's nominal current. That's the value in parameter 08. So if you want to know what it is in amperes, you'll have to convert it. 16,384 or hexadecimal 4000 equals 100%. So you convert the number to decimal, divide by 16,384 and multiply by the value in P08. So let's say P08 is set to 1.8 amps and you get 17 FC back. You convert it to decimal, 6,140. You divide it by 16,384. It's 0.375. That's 37.5% of the maximum current. Then you multiply it by that P08 value, 1.8 amps, and you're drawing 0.675 amps. So that is how you would convert the PI3 word into amps. You'd have to do that with your PLC program. All right, we've talked a lot. It's a lot of information. Let's actually go out there and control a VFD. So we're going to do a demonstration. Now I'm connected up using that gateway, the external gateway. I have an Ethernet IP card in it, and I'm connected up to my MOVITRAC LTE-B Plus on my S-Bus. In our last session, we configured our gateway. What I'm going to do, I'm going to fire up a free tool that SCW makes available, and there is a link to it in the description below. It is called the Ethernet Master Simulator. It is a tool that simulates a PLC, and it lets me test VFDs that are field bus controlled using Ethernet IP or Modbus TCP. I'm going to use that as a demonstration rather than an actual PLC. But of course, if you were doing this in the field, then you would be using your actual PLC. But the Ethernet Master Simulator is a handy tool for testing, and you're welcome to use it if you wish. It is, as I say, a free tool that you can download. So let's do that. Okay, well, we're ready now to go try to control our MOVITRAC LTE-B Plus over the field bus. As you know, we've already configured the gateway. We did that in our last session. We do need to go into LT shell and set up a few parameters so our VFD will respond to field bus control, but that won't take long. So as you can see, I've scanned in here and I'm connected up, ready to communicate with my VFD. First thing I'm going to do is enable real-time edit mode. And then I'm going to pick a field bus control mode. I'm going to change parameter 12 to 4. That is S-bus control with the ramp being sent over the field bus. We want that for maximum flexibility. Now we go to the extended parameters. We need to set a few things. We need to be sure that parameter 15, our control variant, is set to 0. That has just an enable on DI1 and nothing else. Now we go down to parameter 36, our communications parameters. Notice our address is already set to 1. If I needed to change that, I would have to go and do that from the keypad. I also changed the communication speed to 500 kilobits per second and the communications trip delay to no trip. And that is all I have to do. We're now ready to operate in field bus mode. What I'm going to do is I'm going to turn off my VFD and I'm going to connect up my gateway. You can see this picture. This shows you my setup. You notice I've plugged the splitter into the communications port. I've plugged the gateway cable, which is the red one, into one side, and I've plugged the terminating resistor into the other. So I have just one VFD on my network here. Of course, I could connect up to 7 more if I wish, but I won't do that here. So once that's all in place, I'll turn everything back on and we'll be ready to jump into the Ethernet Master Simulator and start communicating. All right, so you can see I've got the Ethernet Master Simulator started up on the right side of the screen. I'm going to connect in just a second with it, but I want to explain a few things. First of all, let me put this little table up here. This is going to help us as we go along because we're going to be sending process data words and they need to be in hexadecimal. So I've gone ahead and I've done all the necessary calculations and conversions here. We're going to operate the motor at 1000 RPM clockwise and 750 RPM counterclockwise. So what I do is I took 1000 and divided it by my motor's maximum speed, which is 1800 RPM. That gave me my percentage. I multiplied that by 16,384, and that gave me 9,102 for the clockwise direction, and then I did the same thing for the counterclockwise. That gave me minus 6,827. I then converted both those numbers to hexadecimal, being very careful to click the minus sign in the Windows calculator so I get a negative hexadecimal number. And you can see my numbers are 238E and E555. So those are my two speeds. Now for my ramps, I decided I wanted a 5-second up ramp and a 10-second down ramp. I converted those to milliseconds, 5,000 and 10,000 milliseconds, and then converted them both to hexadecimal, 1388 and 2710. So those are the values I'll be sending in process output words 2 and 3. And then finally, I've got all my PO1 combinations for different operations. I have run, normal stop, rapid stop, and controller inhibit stop. So I'll be sending these hexadecimal numbers using the Ethernet Master Simulator, and hopefully my motor will respond. And speaking of motor, we better bring that up so we can see it, so we can watch it go. All right, so now we're ready. We'll get connected in the Ethernet Master Simulator. So the first thing I need to do is I need to be sure I'm in Ethernet IP mode. So I double check that I've picked Ethernet IP, which I have, and then I put in the IP address of my gateway. And remember, we're using the SEW default address, which is already keyed in here. I'll click Open Session, and you can see we got connected, no problem. It identifies the gateway appropriately. So that's ready to go. So I will click Start, and that will open my communications. Now you can see I've got my 24 process data words. Remember, we can support up to 8 VFDs. We're only going to work with the first 3 of each because we have nothing else connected there. I'm going to uncheck Auto Update PO. This is very important, otherwise the program will send things the minute you type them. And I prefer to type them and then click Update PO. So that's a better way. So let's go ahead and set up to run. I'll put in the run command, that's a 6. I'll put in my 1000 RPM value, that's 238E. And then I'll put my 5-second ramp value, 1388. Then I will click Update PO, and guess what? The motor starts to run. By the way, digital input 1 is turned on. I have to have that on to enable it. So you can see we're running and we are getting data back in the PIs. Now let's change to the other direction. I'll put in the minus 750 RPM and I'll click Update PO again, and you can see we're going to slow down, stop, go the other way. By the way, don't worry about the PIs too much. They tend to lag a bit behind. That's a quirk in the Ethernet Master Simulator. It won't happen if you're connected up to a PLC. All right, now let's go ahead and go back in the other direction again. I'll put in my plus 1000 RPM. And we slow down and we reaccelerate the other way. That's good. All right, let's do a stop. I'm going to put in my 10-second ramp for the stop, 2710, and I'm going to do a regular stop by putting a 2 in process output word 1. Click Update PO, and you can see we're slowing down. That seems to work. All right, we're going to go back up to speed, so we have to change PO1 to 6, and we have to put our faster ramp in PO3. So let's reaccelerate back up to 1000 RPM, and let's try a rapid stop this time. Remember, this uses a parameter for a quicker stop. It's set, I think, to just a second. So we'll put a 0 in here and click Update PO, and we stop pretty fast. All right, speed up again, and finally we'll try a controller inhibit stop. This just cuts off the output transistors and the motor can coast. It will stop pretty quickly here because I don't have a load on it, so I'll put a 1, Update PO, and it did indeed stop quickly. All right, well that worked pretty well. You can see Fieldbus control is actually pretty simple. Now, of course, if you're writing a PLC program, then there's all the details of that, but the actual tasks you have to do to control a MOVITRAC LTE-B Plus are pretty simple. All right, well, I hope you found that interesting and instructive and whets your appetite for Fieldbus control. I have just one final thing to talk about, and then we will be done with this session. I want to talk about some of the terminal control variants that are available when you're in Fieldbus mode. Remember, when we were in keypad mode, there was a limited terminal control mode available. Well, the same is true in Fieldbus control. Now, I mentioned last time that 8 of the available variants are identical. They simply use digital input 1 as an enable-disable signal, and that many people just jumper it to 24 volts when they're in Fieldbus mode. But there are several other modes that are useful, and I wish to overview 2 of them just to give you a clear idea of what they can do. This is variant 3. This one is kind of interesting. It lets you use an external fault sensor like a temperature sensor or some other kind of sensor. And it also lets you switch between Fieldbus control and a single preset speed. So digital input 1 is the usual enable-disable signal, but digital input 2 selects between the Fieldbus if it's off, or preset speed 1, which is a parameter-based speed, if it's on. Digital input 3 goes to the external fault sensor, and digital input 4, or analog input 1, does nothing. All right, so that is one variant that you can use. And then there's another one that is similar, variant 6. Again, it has the stop-run control, but what this one does, instead of using a preset speed, lets you select between Fieldbus control and a potentiometer. So if you put an off on digital input 2, you run by the field bus, and if you have an on, you run by the potentiometer. Digital input 3 again is a fault sensor, and analog input 1, digital input 4 is the potentiometer. So these variants are useful. You may wish to use them instead of variant 0, which is what we've been using. All right, well, on that note, we are now, at long last, at the end of our course. So this is the end of session 10 and the end of the class. Really good job for sticking with it, for learning a lot about the MOVITRAC LTE-B+. I think you deserve a few gold stars for hanging in there, especially for hanging in through field bus control. So I hope you enjoyed the class and found it helpful, and that you will come back to SEW Eurodrive's YouTube channel and look for other classes. There are plenty of other things to learn about our interesting and useful products, and I hope to see you again in a future class. Have a great day.